Hey guys, I stumbled upon something that I think I got really lucky with. Now I say lucky because I had no idea I was going to figure this out. No idea. Completely accidental. I can take the DH ratios of objects and figure out how old they are. Neptune and Uranus, as opposed to the Earth's DH ratio of 1 over 6,250. So that's right there. And Uranus and Neptune, 4.4 plus or minus 0.4 times 10 to the 5. And then, what's that? Yeah, that's Uranus's and that's Neptune's. If you set those to the age of the Earth, basically what I did is you take those ratios and you pit them against the Earth's ratios to find out how old the object is. And I have Uranus to be as 1.2375 plus or minus 0.1125. That's from the deuterium to hydrogen ratio. And Neptune is between 1.15 plus or minus 0.1125 billion years old. So one's slightly older than the other. I got really lucky, but it also matches with the earlier predictions when it comes to the differences between the two based off their volumetric composition concerning methane and their relative sizes. I originally had Neptune as being 2 billion years old and Uranus is 2.1 billion years old. So the differences in age by about 100 million years I had spot on. And I also had their position in age. So I have Neptune as being younger than Uranus. So the fact that matches their isotopic abundances as well, when you measure the isotopic abundances in terms of each other, and then you look at the objects, it's pretty astounding that that was even there. I guess I got really lucky with that. I didn't even know the DH ratios would match. I was focusing on oxygen and nitrogen. But this is a really, really big deal. There's Neptune and Uranus, I have those. And Saturn and Jupiter, I take their DH ratios as well. Jupiter is 632 plus or minus 98 million years. According to the Galileo probe, it's 731 plus or minus 197 million years old. And Saturn's age is 590 plus or minus 141 million years. So that's down there. And they sit on the graph. I have the younger graph, or the older graph here. Jupiter sits right above Saturn, right above there, and Saturn sits more to the left because it's younger, and below Jupiter because it's less massive. So near the same phase curve, which is very interesting. Of course, I have to figure out numerically the masses on this diagram. I still only have it as a representative line, and that's really cool. I still can't believe it. I didn't think I would get this lucky. I made a typo here on the Mercury paper. Mars's atmosphere, about Mercury. Mars's atmospheric DH ratio, 7.58 over 10,000 to 10.9 over 10,000. And if you set the denominators for Earth at 6,250, and you come up with Mars being 4.74 to 6.81 times older than the Earth. And that being said, if Earth is 4.5 billion years old, that makes Mars 21.33 to 30.65 billion years old. And I previously had in the model Mars being a little bit below Earth, and to the very right below the Venus phase curve, the original Venus phase curve, probably about like right there, probably about right there. So it's technically a recently dead star. That I already had Venus positioned all the way to the right, it's extremely old, Venus is, but Mars is definitely a recently dead object, and I didn't even know that DH ratios were going to match almost perfectly. And the reason why they match is very simple concept to understand. Basically, you have the DH ratios falling off precipitously as the object evolves. So basically we have young stars in the very beginning. Their DH ratio is really high, or really low, I should say. And then as the star evolves, it goes down in this direction. So we can use the DH ratios to determine how old the object is, given the young stars have very little deuterium versus hydrogen, and the deuterium ratios increase. Think of the same way that a centrifuge, when you have a couple materials in a centrifuge and the thing spins really fast, the lighter materials go to the top and the heavier materials sink to the bottom of the tube. Similar to the Earth, similar to stars as they evolve. As they evolve, the lighter materials escape. It's out interstellar space as the mass is lost and the heavier material sinks. So what this is called is whole body mass dependent fractionation. It's called whole body mass dependent fractionation. Whole body because it's the entire star that loses its mass. Mass dependent, meaning the deuterium is twice as heavy as the hydrogen. And fractionation means separation. It fractionates. Basically, fractionation is also, think of like a fraction. You have 1 over 10,000 or 1 over 1,000. That's basically where I'm going with this. I also wrote another paper that we can, oh yeah, I have this on the, I think it's the Uranus paper. I'll read this out to you. That being said, we now have another method to weigh against radioactive half-lives. In fact, we can also use the stable DH ratios to check on the radioisotope claims as well, to cross-examine them, to make sure there is no funny business going on with initial radioactivity being skewed to fit preconceptions. So basically remember my talks about the triangulation when you're looking for something? You have two observers on a field, and you have one observer looking from this direction, and you have another observer going from this direction, and in the center is it's the actual location where you can pinpoint the object where it's physically located. Same thing with this. We can take radio isotope info, and now we can take stable isotope info. So we have stable isotope info and we have radioactive isotope info, and we can triangulate how old the objects are, how old specific objects are, by finding the center where they cross over. As well, what that does is if you have mass-dependent isotope fractionation of the stable ones being completely off from the radioisotope measurements, that means the radioisotope measurements probably started off with a false initial composition for the material. So like when they measure how much, when they do the lead uranium method, and they find a lot of when they find a lot of lead in there and they find a little bit of uranium, they have to assume what the initial uranium amounts were based off of how much they presume based off models that should be. So they can set they can set the initial amounts to be whatever they want to match preconceptions. So maybe they can set it as the entire thing was being uranium, and then there's very, very little left over, and then they can push that age back a lot. Or they can say, oh, well, there was only a little uranium there, and then they can bring the age forward as much as they want. So basically, this is like a cross-check for initial values for the radiometric method. Because what I found is the radiometric is subject to preconceptions based off of, peer pressure. If you're doing radiometric measurements of rocks and minerals and asteroids and what have you, you're not going to be able to publish ideas that say that the findings are exceeding 13.7 billion years, as the paradigm says the entire universe is. So what if it really is a lot older? You're not ever going to get your results published. So what this does is put pressure on those people to report what is actually being found, and it also allows them to have a way to cross-check their initial assumptions. Unfortunately, this isn't going to be accepted, but really, I can use it now because I understand that, or we all understand now who's watching these videos, that these objects are all vastly different in age. And with that in mind, we can actually look at them in a much clearer light. Essentially, we stepped out of Plato's cave now, and we can use stable isotopes to measure their ages. All right, hopefully this helps. If there's any confusion, just contact me, let me know.